I want to talk to you now about pure substances. Pure substances are substances that have a set formula. Now, pure substances will either be elements or compounds. If it's an element, it's going to be made up of only one type of atom. So copper is going to be made up of only copper atoms. Compounds are made up of more than one atom combined together as a molecule. And a molecule would be the simplest form, the smallest combination that retains the properties of the substance. Now, molecules are themselves made of atoms. So atoms are the building block for all matter. Now, some students get atoms and cells mixed up, and the chain of connection there is atoms make up molecules, molecules make macromolecules, macromolecules will make your proteins and your lipids and DNA, and those things will make up organelles, and then organelles make up cells. So cells are the basic building block for living substances, but atoms are the basic building block of all matter, living or non-living. Some examples of atoms would be like hydrogen, oxygen, or even silver. Notice that not all of our atom symbols only have one letter. When we have a second letter, it's written lowercase. Now, an example of molecules would be like water, H2O, or carbon dioxide, CO2. If I had a bottle of water and it had H2O in it, I would call it empty. A molecule of water only has 3 atoms, 2 H's and 1 O. So when we are talking about water in the bottle, we're talking about the compound water that we can see, feel, taste, and touch. Now, we have changed our understanding of the atom over time. And what I want to talk to you now about are the different models of the atom. The very first person responsible for contributing to our understanding of the atom was Democritus. Democritus was a Greek philosopher in the Middle Ages who used his power of reasoning to say that I can't continue to cut something down indefinitely. Eventually, I'm going to reach that point where I cannot cut anything down any further, that indivisible piece. And he called that indivisible piece atomos. And that's where we got our word atom from. Now, Dalton came along in the 1800s, and he made some very powerful statements that changed some of the alchemy practices that were going on at the time. The primary objective of alchemy was to create gold from things like lead and copper. And so what Dalton said in a lot of his statements is that an element is made up of identical atoms, and the elements like gold versus lead have different or unique atoms. So I can't take the lead atoms and change them into gold atoms. Gold atoms look different than the lead atoms. And if I want to get a different substance, the only way to do that is to combine atoms from different elements together chemically. Now, in 1897, Thomson, who is actually a physicist, or was a physicist, was experimenting with gases, and he wanted to see what happened to the gases when he put electricity through them. And what he found out is that this neutral substance, this gas that didn't have any charge, when electricity passed through it, gave off charge, and it was not expected. So I have here that it's the gas experiment gone wrong. He got charge where he wasn't expecting to get any. And so he said that all of these atoms contain this negatively charged subatomic particle called an electron. Now, Rutherford came along in 1908, and he was looking for these electrons. He was doing some purposeful experimentation. And what he did is he took a very thin sheet of gold and he fired some positively charged beam, like a laser light, into the gold foil. And what he was expecting to happen was for the positive to attract to the negative inside the gold foil. But he got some unexpected results. Most of the time, his positive light beam passed straight through, like it had passed through empty space. And occasionally, it bounced straight back onto the source of his laser. And every now and then, he did see that bending of the light that he expected to have. So he came up with the idea that this atom is mostly empty space with a positively charged center, and he called the center a nucleus. Now in 1913, Niels Bohr came along and he said those electrons that you see in the atom that every now and then are there and are occasionally are not, must orbit that nucleus like the planets orbit the sun. So he is the first one that gave us this understanding that there are energy levels that the electrons live in. Now, our modern understanding of the atom is actually called the wave model. And what it states here is that those electrons are in constant motion and their position will change when their energy changes. So we have this beginning of quantum theory where as an electron will absorb energy, it will go from one energy level to the next. And it's in constant motion because it travels at the speed of light. Now, electrons, protons, and neutrons then must be subatomic particles. The only one we haven't heard yet are these neutrons. Protons are positively charged, electrons are negatively charged, and neutrons are neutral. Now, a common mistake that students make is that they want to say the neutron is negative. I guess because the positive goes with the proton P and P, you want to put negative, the N, with the neutron. A better way to remember it is that the neutral neutron is in the nucleus. Put those three N's together. Electrons are negative. A good way to remember that is like a negative election is when you have campaign talking bad about the other person. So negative electron, positive proton, and neutral neutron. Now, protons and neutrons are part of the mass of the nucleus because the nucleus contains all of the mass, and it is called the atomic mass. That's what AM stands for. Now, it's not correct to say that the protons are half the mass because I don't know how many protons and how many neutrons each atom will have, but the way I get the atomic mass is I add my number of protons plus my number of neutrons together, and that total will be my atomic mass. Electrons are in the electron cloud, and they have very little mass, so we don't add their mass to the mass of the proton and neutron when we're calculating the mass of the atom. Now, this proton is the atom's ID. Like you have a social security number that is unique to you. An atom has a specific number of protons, and that number of protons is equal to its atomic number on the periodic table. And if the number of protons were to change, then what the substance is would also change. So carbon has a specific number of protons. If I change the number of protons carbon had, it wouldn't be carbon anymore. Now, electrons are responsible for the atom's charge. If I lose electrons, my atom would be said to be positive. And if I gained electrons, my atom would be negative. Now, a positive ion is a cation, and a negative ion is an anion. An easy way to remember that is if you do negative and positive alphabetically, N comes before P. Well, A comes before C. So the negative is the anion and the positive is the cation. Now, the way I get the charge is I add up the number of protons, which are positive, and I add up the number of electrons, which are negative, and when I sum those together, I will get the charge. If I have more protons than electrons, my atom would be positive. If I had more electrons than protons, my atom would be negative. Now, the neutrons are responsible for the isotopes, and isotopes are all about the stability of the atom. If I have the same number of protons in two different atoms, but I have a different number of neutrons, then I have two isotopes. They are only isotopes as long as they have equal numbers of protons, but different numbers of neutrons. Because remember, if the proton number changes, it's not the same substance anymore. Now, if I have too many neutrons versus protons, then the atom is unstable and the isotope may be radioactive. So let's look at isotopes in a little bit more detail. If the red dots are neutrons and the green dots are protons, which of these atom structures are isotopes? Well, according to our definition of an isotope, the two atoms that have the same number of protons but different number of neutrons would be isotopes. So I have 4 protons here and 3 neutrons, and I have 4 of each in B, and I have 3 of each in C. So the correct answer would be A and B, because both A and B have the same number of protons but different numbers of neutrons. Another way of asking the same question is in a chart format. The pin number is the proton, electron, neutron number for an atom. So if I have 4 different atoms with this pin number across, and the question would still be, which are isotopes, I would have to look at the proton number and the neutron number. The electron number is extra information. There's nothing about the number of electrons in the definition of an isotope. So my first rule is I have to have equal numbers of protons. So 1, 2, and 4 all have 4 protons. But when I look over at my neutron values, 1 and 2 have the same number of neutrons, so they're actually not isotopes, they're identical. They have 4 protons and 4 neutrons. But number 4 has only 3 neutrons, so it has 1 less neutron than 1 and 4, 1 and 2. So 1 and 4 are a set of isotopes. It could also be said that 2 and 4 are isotopes because they have 4 protons and 3 neutrons.